Okay.
The bottom number is the proton.
Yeah.
And then the top is
The top one is the atomic mass. Right here. That's protons plus neutrons. Okay? And the bottom number is, well, I shouldn't have made that line go out there. The bottom number is the atomic, atomic number. That's this number right here. And that's just the number of protons. Alright? Does that make sense? Alright, good. Now, that's alpha.
Can you go back down?
I can. Or in the southern way of saying it, words that only have one syllable are pronounced like they have two. Can. Okay. I can say that because I'm a southerner. Can. Two syllables. Can. It really only has one syllable, but in the South we often say can like it has two syllables.
Oh.
Wait, did you say toucan?
That's what I heard.
Is that a joke?
I heard toucan. I heard toucan too.
Alright.
I would say I heard toucan, but
Alright. Now, if you were really, really, really looking carefully at those particles or those vapor trails in the cloud chamber, you might have seen some that look like this and some that look different. And I saw some of the different ones when I was looking at some of your...
cloudy one.
No, cloudy ones were probably this. Okay? But they... No, that was a streak of light, more or less. Okay? But if you saw one that kind of squiggled, more than likely that was not an alpha particle. In fact, I'm pretty sure it was an alpha particle. That was beta. Uh-huh. Okay. Now, where do we... So uranium doesn't go through beta decay. But if we take an alpha particle out of uranium, we have to get rid of two protons. If I get rid of two protons, what element do I have? Thorium. Thorium also goes through alpha decay. So if thorium goes through your alpha decay, what element do I have? Wait a minute, is that right? Or is thorium goes to beta decay? I can't remember now. Where's that red test? Here, this is a test. Let me look. I'm confusing myself. Yeah. No. Yep. Okay. Hold it. Thorium goes through beta decay. So thorium does something different. Okay. All right. Let's look. Beta. Beta is the Greek lowercase letter b, and it looks like a capital letter B, sorta, but with a tail on it. There's beta. And so we're going to talk about beta decay. That's the Greek letter B, lowercase b. Beta decay, emission, radiation. Okay? So we said an alpha particle was like the nucleus of a helium atom. It's made of two protons and two neutrons. A beta particle is an electron. But where do you find electrons? Not in the nucleus. In the electron cloud around the nucleus, okay? Beta particles, the only difference between the beta particle being an electron and an electron being an electron is the electron is, generally speaking, originally found in the electron cloud. The beta particle comes out of a neutron in the nucleus. Okay? Beta particles come out of neutrons, which have a symbol N. Okay? Alright. If beta particles are electron, what charge does the beta particle have? -1. That's the charge. Okay? Neutrons have what charge? Okay, Houston, stay off your cell phone. I just saw the email you sent me. You had to do it from your cell phone because you're sitting right here. All right. All right. Now I know we got this new thing, bring your own device and all that, but come on, we're in chemistry class right now. Let's focus on this stuff, okay? Come on.
It's like emailing you a question or something.
Were you emailing a question? Are you being difficult? See, let's focus on alpha and beta particles, okay? All right.
What about my beta particles?
Quiet, please. Come on. Quiet, please. Come on. All right. Now, if neutrons are neutral and beta particles are 1 negative, and beta particles come out of a neutron, what do you get after the beta particle comes out? Not yet. Unless you're answering this question. Just hold on. Listen to the question. Listen to the question. This is a complex, multi-step question.
I told them to answer the question for me.
What? Okay. All right, the question is, neutrons are neutral, beta particles are -1 charge. If a beta particle comes out of a neutron, what do we have left? A positive. Beta particles have almost no mass, so what's left is a proton. Now, to write the nuclear symbol then for a beta particle, it almost has no mass. It has very little mass. Okay? So what we're going to put up here if it has very, very little mass? 0. Less than 1. Way less than 1. In fact, this is the mass of a beta particle is 1 over the mass of a neutron is 1 AMU or U. This is the mass of a beta particle or an electron. Almost nothing. So we can put 0 here. Alright? For our nuclear equations, to make the math work out, this is an imaginary number. It's not a real number, but it's a number I'm putting in here to make the math work out. It's a -1. Okay? So -1. What?
I didn't send that email, so I'm not positive.
No, that's a whole different email account. What's your question, Elijah? I don't know. They'll get them to you tomorrow or the next day or something. Once you get them made, you're required to wear them, I think. All right. So we've covered alpha particles and beta particles. Please pay attention. Those are the only particles. Her pass isn't finished. Those are the only particles. The next thing we want to talk about is not a particle in the sense that we think about it in high school chemistry. Okay? The next thing is actually a form of energy. In fact, it's a type of light. Okay? And that's gamma. So we have gamma decay, which almost isn't decay at all. Not in the terms we think of in high school. There's a form of decay because there's a tiny amount of mass loss. Okay? But we're going to ignore that. But we do have gamma emission and gamma radiation. Okay? But this is energy. It's light. Gamma radiation is the smallest of all wavelengths of light. The smallest of all wavelengths of light. It's the most dangerous form of radiation. gamma radiation has the smallest of all wavelengths of light and is the most dangerous form of radiation. X-rays have a longer wavelength than gamma. And X-rays go through, everybody knows about X-rays, right? It goes, yes, it goes through almost everything but your bones, doesn't it? Bones and teeth, right? That's why we can take pictures of your bones and teeth using X-rays.
Oh, and anything bad that
Gamma is even more powerful than X-rays. Gamma will go, gamma can damage your DNA. Okay? But there's gamma in this room. There's gamma coming out of those uranium ore samples. Because, here's the thing. Listen. It's all a matter of how much. Your body is designed to repair. And it's a self-repairing mechanism. Okay? There's gamma all the time, all around you, every day. Alright? You can't get away from it. It's not possible. Please don't pack up till I tell you. Okay? It's all a matter of how much. But now gamma symbol is this. And since it's light, how much mass are we going to assign to it?
0.
No mass. And are there any protons? No protons. It's not going to change any of the particles in the nucleus. So we'll give it no protons. Okay? Kind of. It's like a script L that you spun around. If you turn your paper upside down, there's a script L. Flip it around, you got gamma. Okay? Alright, now you can pack up. Please don't pack up till I tell you it's okay. Alright, guys? Did somebody say yes, ma'am?